So this tutorial is going to focus on another enzyme mechanism, this time specifically for carboxypeptidase A. And again, this is an enzyme that we've mentioned previously. A carboxypeptidase is going to cleave a single amino acid residue at a time from the carboxy terminus of a peptide. So here we have a phenylalanine residue at the carboxy terminus, and then the rest of a polypeptide chain. I've just abbreviated R here to simplify everything. And as we've talked about previously, this squiggly line is just kind of outlining the active site of this enzyme. And here we've got significantly more residues playing a role in this catalysis. But once again, the whole point here is to hydrolyze this enzyme, or this amide linkage in the polypeptide backbone. So you can see that we've got some arginine residues that are going to help orient the molecule. We also have histidines and a glutamic acid here that are actually coordinating a zinc ion. And the purpose for this is to increase the nucleophilicity of this water. So by coordinating water to this positive charge, it allows this glutamate to act as a nice acid catalyst, easily pull this proton off. Being near this positively charged zinc is going to significantly decrease the pKa of this water as an acid here. And then it's going to make a much better nucleophile to attack our electrophilic center here. We're trying to break this bond. Okay, so our glutamate can grab that proton. This electron pair then can act to attack our electrophile, put electron density out here, which is going to be stabilized by the presence of this arginine. And my little note popped up here, and I kind of already gave away the point of the zinc is going to help decrease the pKa for this water, make it deprotonate to OH minus to make a better electrophile. So we generate this transition state, which again is stabilized by the presence of this arginine. Once this falls apart, so this tetrahedral intermediate reforms the carbonyl, that means this bond is going to break, and we're going to pick up the proton that we gave to the glutamic acid here in that procedure. And what we end up with is this phenylalanine residue in this case, and the carboxy terminus of the new carboxy terminus of our peptide. But we can actually get a proton transfer here, and we can show this either being mediated directly through these two pieces or through a subsequent water molecule, right? Get NH3 formed and then OH minus formed on the carboxy terminal part of our peptide. So I'm just showing it this way. Now we have a free phenylalanine residue in our new peptide, and everything in the enzyme now is reset back to where we expect it to be able to bind another substrate molecule and go on through another series of reactions.